Okay, we are recording now. So again, welcome to the New York State Bluff Symposium. We'll get myself situated here. Sorry. Your screen. Here you are. And I'm going to start sharing my screen. Okay, so once again, welcome to the symposium. Today we're going to have a couple of speakers present. We're going to start with our welcome and an update on the new New York Sea Grant Bluff resource. That will be done by myself. I'm Kathleen Fallon. I'm the Coastal Processes and Hazard Specialist at New York Sea Grant, located on Long Island. And Roy, who I'll let you introduce yourself in 1 second. Then we'll turn it over to Drs. Ali Farhazadeh and Henry Boknievich from Stony Brook University, who will give an update on the erosion and recession of coastal bluff research that they are conducting. Then we'll turn it from there to David Klein and David Clark. David Klein from the Nature Conservancy, David Clark from the DEC, who will talk about the Army Corps Lake Ontario sediment budget projects. And then lastly, we'll switch to Danielle and Dana Rose from the Army Corps of Engineers, who will talk about their North Shore of Long Island Regional Sediment Management Investigation. So with that, Roy, you can take it away.
All right, thank you, Kathleen. So I want to, well, I'll introduce myself to the downstate folks. Everybody up here should know who I am at this point. So I do the same thing that Kathleen does, just up on the Great Lakes, so Lake Erie, Lake Ontario, and the connecting waters. And over the past probably 8 months or so, Kathleen and I have been working on what we are calling the Blufflet. So this is an extension of the Farhadzadeh and Bakunowitz omnibus research proposal that we funded a few years ago at this point. And what it is an 8-page booklet with annotated bluff processes and shoreline erosion monitoring resources. And this is aimed mostly at not just residents of New York State's bluff shorelines, but also land managers, parks, public property, permitting if needed. It's not a permitting document, but it could be of use to pretty much anybody working and living up in the Great Lakes. This is in the very final stages of review, both internally and externally through New York Sea Grant. So we hope to have this published and printed by mid-December at the absolute latest. We need maybe two or three more reviews, and then we're good to go to push this out. There will be a digital version and a printed version. And I think that's it for the intro. Let's keep moving. So what we really wanted to do with this is to explain some of the mechanics of bluff erosion, both on Long Island and up here in the Great Lakes. So this is kind of the centerpiece of the whole thing, and it's detailing a lot of different processes that affect our coastal bluffs in New York State. So overland flow, bluff crest erosion, disturbances from people and animals, slumping, toe erosion. Essentially anything that can happen to a bluff. We wanted this to be a nice visual explainer of it. And it says work in progress by Joel Davenport, but this is very close to finished, and we are pretty excited about it. A little bit more about the content that's within it. So there's an introduction just to the coastal bluffs, their extent, and what they're made up of in New York State, both Great Lakes and Long Island, the processes that are affecting those bluffs, and a lot of visual interpretations of this. So we scour pretty much all over the shorelines of Long Island and Lake Erie and Lake Ontario to find the best examples of these processes going on, and they are pulled out and with high resolution photos throughout. And we did want to talk a little bit about how the bluff movements are usually episodic and driven by high water, storms, sea level rise, freeze-thaw cycles, especially up here in the Great Lakes, and increased runoff, groundwater, and how humans kind of can influence the rates of bluff erosion as well. So we did want to add a little bit about monitoring and reporting bluff erosion. So we do have an insert that was actually originally developed by Megan Coker, who's up here in the Great Lakes with me. That was originally put in these landowner folders for Wayne County, actually. So we had Joel edit that a little bit to provide a resource for residents and shoreline property managers to both monitor and evaluate how their shorelines change over time. So there's not just the centerfold that is in there that you saw a few slides back, but also a monitoring, not a protocol, but a way to monitor your properties up in the Great Lakes and on Long Island. So that's that'll be put in there as well. I don't think we have an example of that though. Right. So that's the record keeping insert. It's essentially a way to map your own property on this kind of gridded format and monitor how much the shorelines change over time, and also develop long-term plans and foresee potential issues, erosion hotspots on properties, and to record significant events and impacts. So if it's, you notice it happens every spring at a certain time, or if you're maybe on Lake Erie where it happens with the gales of November, which should be starting up soon, with the SAISH events and everything, that's a good way to teach people that this is kind of the mechanics of how everything happens. We also wanted to stress that we do still have our bluff erosion reporting websites up. So these are survey 1, 2, 3 links, and they let you take pictures of shoreline erosion anywhere and upload those and talk to a New York Sea Grant representative, either Kathleen or myself, about the erosion and managing erosion on properties. This is, you want to take it from here?
Sure.
Okay.
So this is the contact information for all of the presenters today. Myself and Roy at New York Sea Grant, Dr. Farhazadeh and Bokmievich at Stony Brook University, Dave Klein at the Nature Conservancy, and David Clark at DEC, as well as the Army Corps of Engineers, Dana Brown and Danielle Amaso. So feel free to contact and reach out to any of these people with any of your questions afterwards. We are going to switch it over, and I will pass it over to Ali to start his presentation. So I'll stop sharing. Ali, you can get situated. And in the meantime, I just want to remind you that if you have any questions, feel free to put them in the chat. And our presenters can answer them in the chat, or we will be doing kind of a panel discussion, question and answer session at the end of the 3 presentations. So thank you. And Ali, you are good to go.
Kevin, is this in a presentation mode now? Or?
And not yet. I can see your screen, but it's not in presentation mode.
No, no.
Not yet.
good now?
Yes, you just need to switch it to presenter, to hide the presenter. Yeah, if we click the three dots.
Mhm.
and- Oh, oops, it stopped sharing again.
I don't know what's going on here.
Okay, you're good.
Good. Okay.
Yep.
Good morning, everyone. My name is Ali Farhadzadeh. I'm an associate professor here at Stony Brook University, and I'm presenting the work that we have been doing with Dr. Bukanjanovic and a number of grad students over the past couple of years, funded by New York Sea Grant. And the objective of the work is to basically, as you can see from the title, to understand how soil properties impact the erosion and recession of coastal bluffs. Our work is not particularly focused in particular New York. It's more of a fundamental research trying to understand how processes related to soil that they intersect with wave and water level would impact the behavior of bluffs and also flat beaches, basically the soil property impact on the erodibility of the soil and recession rate. So the outline of my presentation is I'm going to present motivational introduction, objectives, results, conclusion, and what we are currently doing and what is the next step in our research. So as I think everyone here in this meeting knows, coastal bluff is a major issue, and it's a complicated process too. It involves various processes from morphodynamics to soil mechanics, and if you're in Great Lakes area, you have ice issues, freeze, thaw, and all those processes. So it makes it very complex and challenging problem. And obviously, we are not here to solve all these problems, but at least try to understand what's going on, at least from certain perspectives, and see how we can use that knowledge to reduce or manage the recession rate, or at least be able to predict what's going to happen to the bluff shoreline. And the main issue is it's not like sandy beach where you can nourish and have the beach back. This is when the land is lost and it's lost forever. So in the case of bluff recession. And a lot of houses, infrastructure are near that kind of shoreline, a bluff shoreline. And there are a lot of economical, social, and environmental challenges that could happen in the aftermath of bluff erosion. It's a major issue because it also covers a wide part of the shoreline in the U.S. As you can see in the table, certain percentage of shoreline in different part of the East Coast, West Coast, Great Lakes, they're bluff type shorelines. So it's an issue, it's a major issue in many parts of the coastal U.S. This shows an image of Long Island North Shore recession and how the shoreline recessed or retreated since 1947. And obviously, this is not up to date. It's 2016 is the end, but its recession rate is about 0.2 meter per year, which is about like a foot or less than a foot, right? So it could be over many years. It could be significant recession amount. This shows a familiar site to us, at least, near Stony Brook. It's in Port Jefferson. You see an image of 2016 on the left of Fort Jeff, this facility is a clubhouse, and tennis court and so on. And on the right, you see what is the situation just recently. And the bottom picture shows the front of the bluff, basically how it looks. The causes of recession, are different depending where you are, but the behavior of the soil is pretty much similar. So if you're under heavy precipitation, wave impact, freeze and thaw, they all have to do with the behavior of the soil and how it could be affected by those processes and lead to recession and failure of the land. This is an image from, I think, Lake Ontario, as you can see in the caption. It's a disastrous situation. But this is 2017. I don't know how it looks like today. The main issue or difference between the bluffs on Long Island and Great Lake is that the type of soil that we are facing, in addition to the processes from the soil perspective, basically. On Long Island, we have nearly 80% sandy bluffs with 20% or less fines that include silt and clay. In Great Lakes, it's other way around. So you have like 80% till material and then about 20 or less than 20% of sand inside the soil. The process is also different. As I mentioned, you have a freeze and thaw, you have sage, particularly on Great Lakes, especially on Lake Erie and Ontario. And ice impact also is a major issue. The wave is common on both Long Island and Great Lakes. Although the type of wave we have on the north shore of Long Island is different from the south shore, but we still have both effects. This introductory flow chart kind of shows how complex the process is. The blue are related to sea land or sea base processes, wave, water level, storm surge, and the left is the land processes. What happens on the land that leads to bluff recession, seepage, runoff, weathering, and all of these, again, as I would like to reiterate, have to do with how soil strength is reduced, and that means the bluff failure is going to. So basically, at the intersection of these two flow charts, we have the soil strength reduction, which is going to lead to failure. So whatever can be done to strengthen the soil or reduce this reduction of strength or manage the reduction of soil strength would help maintain the bluff. Again, this is another schematic showing various complex processes. You have erosion of the toe, down cutting, as we call it. You have the precipitation, infiltration of the water from the top or the groundwater that is trying to, go through the seepage into the ocean. And all of these going to lead to less of bonding, basically, among the particles, and eventually disintegration of the soil structure fabric. So what we did here is basically to look into a number of soil parameter, the amount of fine particle, silt and clay, the packing or relative density, as well as the water content in the soil and how they would change the strength of the soil. We looked at the processes of erosion and recession, both basically on the flat bottom. We look at the erodibility of the soil and how these processes, the indices, the strength indices there, which is manifested itself into fine content, relative density, and water content, and basically the shear strength of the soil would impact the erodibility of the soil.
Yeah, but what do you think? Whether that's
Microphone is open, yes. So what we did was we went to Montauk Beach, permit from New York Parks, to collect enough amount of soil and use it in the lab in an engineered way, basically. So we went. This is the site. These are the students. I think myself was down there digging the soil. I'm not in the picture. Someone else took the picture. And then we took the soil. It was like a couple of tons of soil. So we had to take them to the lab. We did this sieve analysis, all the index tests to understand what type of soil we are dealing with. These are the table basically shows the variation of different soil properties from the collected soil. We did the Atterberg test limit, triaxial test, and sieve analysis and Proctor test to get the strength indices of the soil. And then we basically re-engineered, reconstituted the soil to reach certain properties. You know, we added to the sand that we extracted from that collected soil 0, 5, 10, 15, 20% of fine particle, again from the same soil after separating it with analysis. We mixed them with the either 7% or the optimum water content. So basically get two different water content. And we packed them at two different relative density, 39 and 68%. And we constructed our sample for both erodibility test and bluff recession test. So these are the details of what we did in order to reconstitute the soil. So I'm not going to spend too much time on this. These are the gradation curve for all these soil that we reconstituted. 0%, 5%, 10%, 15, 20% of fines. So basically that means 100% sand, 95% sand, 90, 85, and 80% sand. And then we did the Proctor test. And these are the dry weight of the soil versus water content. And obviously, optimum water content for different soil mixture is different. We did the triaxial test to get the effective cohesion and internal friction angle, which are basically two important parameters into soil shear strength for 20 different combinations. So what you see here, W, that reflects the soil mixed at their individual optimum water content. And on the left, you see the soil prepared at 7% water content, which is basically dry of optimum for those familiar with soil mechanics. So it's a dry soil versus optimum or optimally moistured soil. So these are basically the results of triaxial test, and you see the specification of each soil sample. So these are the dry soil, 7% water content, and 39 and 68% relative density. These are the soil prepared at the optimum water content. You see the different effective cohesion and also their packing, bulk density, which is obviously different from the dry soil. So then what we did was we did the steady state flow test. This is a unidirectional flow. So you have a pump, you circulate the flow steadily at certain rate, at manageable rate, whatever you want to do. We prepared the source sample at those packing ratio and water content, initial water content, and placed them at the bottom of the flume. And we measured the velocity profile and as well as instantaneous elevation of the erodible bottom, basically, which is this brown rectangle or square. So the curve at the bottom basically shows, the left axis shows the velocity of the mean velocity. So we basically increased the velocity incrementally until we saw that the bottom or the bed is being eroded. And that erosion is reflected in this brown or red line here. So you see there's a, and the right axis is basically showing the elevation. So the elevation suddenly dropped. So we call this initiation of erosion, and we had the velocity profile measured at that particular moment for different soil. And we came up with these near bed velocity profile. We had to repeat tests each time in order to make sure the repeatability of the test is reliable. So this shows the velocity profile normalized by the mean velocity, and the vertical axis shows the elevation of from the bottom normalized by the depth of the flow that we had for that particular moment. So we calculated the critical shear stress and normalize them to create or add our data to the existing shields diagram. So this is what you see, different data from different people, different years on top. And those in the box are what we generated out of our test. So it kind of complement the existing shields diagram. And we were able to develop a multivariant regression curve, which basically modifies the existing shield parameter to account for the amount of fine particle, the soil composition basically, and packing, the relative density, as well as the omega, which is here the moisture content ratio or the water content. And this curve on the left basically shows how the shear strengths of different soils of different composition, packing, and moisture varies as a function of fines content. So I'm going to go over some of the results. And the left and the right one basically shows the dots are the actual measured data, and the line is the 45-degree line is basically the formula we developed the model. So some observation or conclusion for this part of the study is that the critical shear stress is linearly increased with the fine content. So as you add the fine content, so the soil that has more fine content, more clay or silt, is stronger. It's harder to erode. The soil compacted at their optimal initial water. So the drier soil is more erodible than the soil that has an optimal amount of water, because of the binding and how the particles are integrated together would be different. The higher density or the packing appears to be a major factor. So if the soil is pretty dense, if you have a cemented, for example, soil, it doesn't matter how much fine or clay you have inside the material. Again, our goal or our objective was very low fine content. We didn't go to 80% fine content. So we remained within 0 to 20% of fine content. So our results are valid within that range. So if the soil is packed, then it doesn't matter if you have 5% or 10% fine in the soil. So it's still going to be a major factor, the relative density, the packing, the compaction is a big player. So, and if you have a soil which is dense and it's compacted at the optimum water content, that's the best scenario. You have the highest resistance against erosion. And the fine content appears to be correlated to the effective cohesion. So basically the strength increases with both fine content and effective cohesion. And then eventually we developed this empirical relationship that I showed you. This next set of tests that we did is to take the similar soil that we did the erodibility test into the wave tank, smaller scale wave plume, and build the bluff, again with different soil composition, compaction, and initial moisture, and expose them to wave effect and monitor the soil, the bluff erosion behavior, basically. And it used a non-intrusive techniques to constantly capture bluff profile as it evolved, and to be able to kind of understand the behavior. So this is the small flume test that we did. You see the camera here, and this is a few, probably a minute or an hour after the test was started. You see the water got muddy and the wave is breaking here. And this is so you see initially we had a planar slope. Now you see the formation of sandbar, which is basically the soil was eroded from the beach and deposited offshore. And it started cutting the toe of the bluff. And so this is a procedure we went through to build the model, and all the steps we took to capture the profile and the water level and wave that we had. So we incrementally, we prepared the soil sample, we submerged it for 12 hours. The water gets through all the soil particle like what it is on the beach, at least to some extent. And then we set the water level a little bit below the toe of the bluff, around the wave for 12 hours. After a while, after 12 hours or less than 12 hours, the beach and bluff become equilibrium. There is no much erosion happening. So then we elevated the water for another centimeter. We increased the wave height slightly, and then we ran for another 12 hours. Start eroding again, reaching equilibrium state, then we increased it up. So we tried to model some sort of, you can think of tide or storm scenario, a rising water level, or maybe you can call it sea level rise scenario. And until the equilibrium state happened at the phase 3, which obviously in some cases we had failure of the bluff, in some cases we didn't have failure of bluff. So the equilibrium was basically reached whatever failure or non-failure state we had. But I'm going to show you some of the results instead. So I hope you can. So this is a kind of a fast forward or a speed, the high speed video. So you see the bluff falls down, the sediment is washed, the debris basically, and you see the formation of the sandbar. So basically it's moved backward offshore and build a sandbar offshore. And it reaches an equilibrium state of beach because it's hard for the wave to reach further landward to take more soil out of the bluff. So we have to increase the water level to reach a new equilibrium state. Obviously, if this assumes the soil property, there is no land-based process. If you have precipitation, that might lead to failure as well. But in this case, we are not changing anything on the land side part of the bluff. So everything is remaining constant from the soil properties. So this is showing kind of phases of bluff erosion. So initially you have erosion of the beach. So A, B, C, this is how the clockwise kind of view. Then you have the notch formation, the down cutting of the bluff. Then you have this failure of the overhang. This is a particular case where you have a tensile failure. We don't necessarily have tensile failure. This is for a stiffer soil. This is the process. I'm going to talk about this in a second. And then this debris that is deposited here in image 3 or C is going to be eroded and deposited offshore. And now you have an equilibrium state. So nothing else would happen until you rise the water level again. And that's going to be back to panel A. And then we have another cycle. This is the way we use the image processing to extract the profile. So you see calibration on the left and the kind of an angle view, and then we projected them to the flat view and extracted in panel C on the right-hand side the actual profile of the view. And we had it every few seconds. We had images and we were able to extract the profile for every 30 seconds or so. And these are basically showing different soils. So L stands for loose, D for dense, and 0, 5, 10, 15 stands for different fines particle in it. And the profile you see here is after 12 hours, after 24 hours, after 36 hours, which is the final profile, and the brown is the initial profile we have. So you see different kind of notching happening. When the soil is denser, you have the formation of notch on the right-hand side. Those are all the highly packed soil, basically. And when you have a looser soil or less amount of fines in it, the failure is mostly shear failure. So the whole body basically fails altogether. Not you cut it through and overhang. That would be for a denser soil, or the soil compacted at optimum water content. So this is W stand for those soils that were compacted at the optimum water content with different density and different fine particle. So this is two particular cases. The top is the soil with 0 fine, and it's packed at the loose packing density.
You can go get the mail. Maybe the ink is in there.
Okay. The bottom one is the denser soil, and you see one point that I was going to mention here. This dotted line, the thick dotted line, shows the equilibrium beach profile. So here, when the soil is more sandy, you have a concave up, which is a typical beach profile we are familiar with. And the one when you have a dense soil, the beach profile is concave down. So it's like it's curved downward, basically. So this is the main difference between the two profile that you will see when you have soil of different strength. The type of failure for loose soil, dry soil with low amount of fine is more shear failure, and the rest you see there are tensile failure, and obviously for the shear failure you have a larger amount of recession. The soil gets stiffer and denser, and with the optimum water content, the amount of recession is reduced significantly. And this shows how the recession rate varies with different, the red is basically showing as a function of effective cohesion, and the bottom axis shows the horizontal axis shows the amount of fine, basically, how increasing the amount of fine particle in soil would change the recession rate, which is the axis on the left and right, the vertical axis. So it's clearly with the adding more fine to the soil, or the bluff that has more fine in it, they will resist more or less failure, but also the impact of compaction. So if you go toward DR68 and also optimum water content, you get much more resistance in soil, and that would lead to much less erosion. Okay. We developed the relationship for the recession rate as a function of those variables. As I mentioned, the amount of fine, the relative density, and the moisture. And this shows, the dot shows the measurements, and the dotted line shows the formula. So they're pretty consistent, at least the behavior-wise. A few conclusions. Episodic failure, slope failure was reduced as the mechanical strength of the soil basically increased, and that would increase with the more fine content and reaching the water surface or moisture to optimum amount. Recession rate of bluff decreased with the increase of effective cohesion, which increases with the fine content. The trend of the recession rate with respect to effective cohesion was similar to that of the recession rate with the fine content. So again, as I mentioned, this is the erodibility test. The recession rate increases with the effective cohesion and increases with the fine content. They're correlated. So the fine content, more fine content means more effective cohesion when you do the triaxial test. The effective cohesion had a more significant impact on the recession rate when the soil is loose. So if you don't have the packing, good packing factor in the soil, then if you have more fine in it, it should be strong enough, at least to some extent. And we developed this predictive recession rate formula, which include these 3 factors in it. And we also, because we had a limited test done, we did the Monte Carlo simulation to look into the uncertainty range. And the result was pretty consistent with our conclusion that I mentioned about. So again, the relative density seemed to be the most important factor in reducing the soil or increasing the soil, the bluff failure. If you have very dense soil, it's hard to erode. The next step is we are going to run larger scale wave tank. This is a wave tank we have at Stony Brook. It's 85 feet long plume with a 1.5 or 5 feet wide, 5 feet deep. And we are building the bluff in the tank. You see the wood, the lumber, and those plywood that we already placed. You're going to use soil, compact them at layer by layer to build this bluff that you see on the top right schematic, and expose them to wave impact to kind of look into the scale effect as one issue that someone may raise, because our previous test was very small scale. Then we are going to upgrade an existing process-based model of seashore, which I was part of the developing team when I was grad student at the University of Delaware. And we are going to implement the soil strength parameter and the formula we developed in this model so that we can validate it for larger scale tests at the lab, or if we find good quality bluff profile pre and post recession, we should be able to validate it using those data. So we welcome any field scale survey data for bluff, not necessarily just the recession rate, the actual profile of the bluff and how it evolved over time. If there's such data, that would be great to have. That would strengthen our study. We published 2 journal papers this year on this topic. One in International Journal of Sediment Research, the other one Ocean Engineering. And we have a bunch of conference papers. The latest one is the one I'm going to present in a couple of weeks in Australia, again from the same research. And I would like to thank UFC Grant for the funding, and also my current and former student who helped conducting this research. And also thanks to Henry for his continuous help and input. With that, I think I'm going to leave it for question, but I guess I leave it to Kathleen to decide how we're going to proceed.
Thanks, Ali. I would say we're doing great on time. So if anybody has some really burning questions, feel free while we switch presenters, go ahead and you can unmute yourself and ask any question or raise your hand, whatever you prefer. And then only if you can, hi, Henry, go ahead.
I just like to add that one of the things we're looking at, we're starting to look at are hotspots. And this erosion, he mentioned 2.2 meters per year in that one spot, but of course it doesn't happen in a slow, continuous manner. It happens episodic. And there are definitely some hotspots along the coast where it seemed to be more susceptible. Part of that, as Ali was saying, may be due to composition. So we're starting to look at the distribution in light of these mechanical properties and see if we can explain why there are some hot spots and maybe predict where the next ones are going to show up.
Yeah, that's a great point, I think.
Thanks, Henry. And Aram was questioning East Hampton. I don't know if he was asking about it being a hotspot or for a field study. Aram, if you want to clarify or otherwise.
Oh, hi Kathleen. I'm sorry, I was sending that out to Henry. He
Ah,
asked about a particular program, sorry.
no problem.
Yeah, it's East Hampton.
All right. There's any other questions? Otherwise, Ali, if you want to stop sharing, so Dave Klein can start. He sucks that up. And in the meantime, if you come up with more questions, you can enter them in the chat and we will revisit questions at the end of all of the presentation. All right, go ahead.
All right, at this point, we're going to work into some of our local focus about what's going on up here in the Great Lakes. So at this point, I would like to introduce David Klein, Senior Field Representative from the Nature Conservancy. He's going to be talking about the bluffs up here in the Great Lakes and the Army Corps sediment budget. And he is going to transition his presentation into one with David Clark. He's from the Great Lakes program from New York State DEC. So David Klein, if you'd like to start whenever you're ready, we're good to go. You are muted though.
I have a message, Your Royal Sexiness.
Oh. Oh.
Hi, I hope I'm sharing my screen now.
Yep, we could see the presentation, but not in presentation mode yet.
Okay, I'll try to, I hope I'm not going to run into the same problem that Dr. Farajide did. Let's give this a try.
Looks good.
How's that?
Great.
Okay, well, thanks. Good morning, everybody. I know I'm speaking to a large number of people who are pretty familiar with the Lake Ontario southern shoreline. I want to talk about a crucial natural process that operates under the radar and is still poorly understood. And that is the longshore current, the flow, the longshore flow that flows basically from west to east along the Lake Ontario southern shoreline, starting from the Niagara River flowing west to east, maintained by prevailing winds and wave action, the direction of prevailing winds and wave action. And this longshore current carries with it the coarse sediment, the sand and gravel that erodes from portions of the shoreline is carried in this longshore current as the raw materials that builds the beaches and barrier bars that are key features of the shoreline. And as I said, we haven't known much about this, about the dimensions of this longshore flow until recently. And various Army Corps of Engineers analyses have enabled us to quantify how much is flowing and what its constituency is. And what you've got here on the screen is a tiny portion of this sediment budget. This quantification has been called the sediment budget for Lake Ontario. And as you can see, it consists of a continuous chain of 1 kilometer units all along the shoreline. And I'm going to pause for a second and just look at the inflows and outflows from one of these 1 kilometer units. So it's a continuous chain of 1 kilometer units along the shoreline. And we're looking here, everybody can see my cursor. I hope my cursor is visible. What we've got is, this is the 1 kilometer unit in front of Camp Beechwood, which is a beautiful state park property near Sodus Bay. What we see, what the sediment budget is telling us is that the eroding bluffs in this 1 kilometer cell are contributing 8,300 cubic yards of sediment to the longshore flow every year. And of this amount, 5,400 cubic yards are fine sediments, the clays and the tills that are swept by wave action out into the deep lake for deposit. A further 600 cubic yards are coarse sediments that are lost to the longshore flow via wave action. But even with these losses, this 1 kilometer cell is still making a very large contribution to the adjacent cell, which in turn is making, it's contributing 2,600 cubic yards to the longshore flow. And this cell itself makes a sizable contribution. Our Army Corps budgets have shown us that this longshore flow of sediment of the raw materials has been much diminished in the 20th century by all the upcurrent shoreline hardening and engineering that has cut portions of the shoreline off from the lake. It's been much diminished. So this budget is giving us an awful lot of information, but it's very hard to step back when you're looking at 1 kilometer by kilometer. It's very hard to step back and get a whole shoreline view. I'll return to that in just a second. So all of us who have visited the shoreline, you've seen beautiful sites like this. This is the sandy beach at Rosie's Marsh in the Braddock Bay Wildlife Management Area. Well, where did the sand come from? If we want to continue to enjoy beautiful places like this, we need a much deeper understanding of the movement of sand that built this beach and the steps we need to take to safeguard this crucial coastal process. Here's another beach that is formed in front of shore protection structures along Edgemere Drive in Greece. Where'd this sand come from? It wasn't there already, just waiting for the lake levels to get low enough. This sand flowed in the longshore current from a source. Where? Crucial questions if we want to see beaches like this continue to protecting property from waves in the future. Here's a potential source. This is the enormous sand deposit at Lion's Head, at the Lion's Head feature on the western portion of Hamlin Beach State Park. Could this be a feeder bluff supplying raw material to places like Rosie's Marsh and Edgemere Drive? This is the kind of question we need to answer as we consider further steps in management of the land-water interface, the shoreline of Lake Ontario. Well, we've been able to access the data in the Army Corps sediment budget and color code the 1 kilometer cells. So each one of these colored dots is one of these 1 kilometer cells. Color code the 1 kilometer cells. And in this case, we're color coding the cells based on the extent to which the shoreline in each 1 kilometer cell has been hardened through riprap or other engineered structures. And our attention is drawn to the southeastern quadrant of the lake. Follow my cursor, which still appears to be relatively unhardened, intact. Well, what else do we know about this? What else do we know about this region of the shore? Its major geographic feature is the large number of great glacial drumlins, huge piles of sand and gravel and glacial till deposited by the last glacier. So the eroding shore is now interacting with a large number of these drumlins, which form the bluffs whose erosion we're talking about today. It's important to recognize that this erosion is actually performing a key ecosystem function, a key ecosystem service by supplying the raw materials that maintain the beaches and and barrier bars that are such recreational amenities for so many people. This movement of sand and gravel also builds the protective features, the barrier bars that shield property from the full force of Lake Ontario. Here's another view of the lake shore. We've color coded the 1 kilometer cells based on the proportion of soil in each cell that is coarse sediment, sand and gravel. And again, our attention is drawn to the southeastern quadrant of the lake, where there seems to be an awful lot of cells, awful lot of bluffs containing shoreline building materials. Well, what else does the sediment budget tell us about how much sediment is actually moving and where? In this map, 2 areas of the shore stand out. The shoreline, interestingly, beginning with the Lion's Head feature at Hamlin Beach, the shoreline west of Rochester, but also this southeastern quadrant of the lake. Can we use the Army Corps sediment budget to identify areas of the shoreline that seem to be providing key sources of coarse sediment? Here our attention is drawn to Hamlin Beach itself, State Park, the Durand-Eastman County Park, Camp Beechwood, Chimney Bluff State Park, and above all, the Lakeshore Marshes Wildlife Management Area, the units of that, but also Sterling Nature Center jumps out as an important area of the shoreline. Can the budget tell us something about areas of the shoreline where this longshore flow is being deflected into the deep lake? So our attention is drawn to Point Breeze, the mouth of the Genesee River, mouth of Irondequoit Bay, Sodus Bay, and the largest diversion appears to be Little Sodus Bay. And again, these are jetties. These cheap deflecting locations are the major jetties that have been built in several locations. So in this slide, I'll segue to David Clark. But a couple of things I want to point out. This is one of the eroding drumlins. This is Broadway Road, I believe, in the town of Walcott. So to the right, west of this road is a unit of the wildlife management area. And to the east of the road, to the left, are private properties. Fortunately, at this point, no major structures right on the lip of the bluff. Here we also have an intact barrier bar, which is shielding a bay mouth and also extensive areas of coastal wetland. So evidently there's another eroding bluff just to the right off this picture that's supplying that barrier bar. So with that, David, I'll segue to your part of the presentation.
Thanks, David. Yeah, thanks for that overview of the Nature Conservancy's evaluation of the Army Corps sediment budget. There really is a lot of information that can be pulled from that tool. So I'm going to transition a little bit to what we've been referring to as the Southeast Lake Ontario Sediment Study, which geographically overlaps with those regions of high input that David showed on his earlier slides. And this study is intended to build off the Army Corps budget and really has the goal of further advancing our understanding of the regional sediment sources, sinks, and pathways. We're really at the very beginning of this effort, but the idea was really born out of the discussions between TNC, DEC, Sea Grant, and other partners about the conclusions and questions that David just identified. So first, I just wanted to kind of take a quick step back, and David covered some of this, but really just ask a fundamental question. Why do we care about these sediments that are eroding from a bluff, like in this picture? Well, an obvious question would be, if your house was at the top of this bluff, then certainly you would care. And that's a very real concern. But aside from that, and expanding upon what David mentioned, is that these littoral sediments do provide ecosystem services. And these ecosystem services have intrinsic value, even if they're not always accounted for in shoreline management decisions. And this value is often amplified in an area like Lake Ontario, which by and large is sediment starved compared to marine environments or even other Great Lakes. So it's easy to visualize from the photo on this slide that there could be a direct connection between the sediment supplied from this eroding bluff and the adjacent wetland baymouth barrier bar complex. When we consider these wetlands from various indicators related to fisheries, birding, recreational opportunities, we know that they have tremendous value. In general, an intact sediment supply will contribute to the geomorphic complexity of the shoreline, which is really what provides the background of varied habitats. So the baymouth barrier bar protects and allows the wetland to exist due to shielding from the Lake Ontario environment. It has been well documented that reduction in sediment supply as a result of ongoing shoreline armoring has impacts on nearshore beaches and barrier bars. For example, it was determined that reduced sediment supply was a key factor in the degradation of Braddock Bay. And the Braddock Bay restoration project was completed at approximately $11 million. Similarly, there have been other proposed barrier bar projects in Lake Ontario with a wide range of costs, anywhere from a few $1 million up to 14 or more $1 million. It's very likely that reduced sediment supply played at least some role in all of these. And so from this, it's easy to see how an intact sediment supply will increase natural resiliency. Another way to consider the value of sediment supply is from a simple cost to replace perspective. For example, based on the Army Corps sediment budget analysis, the bluff in this image is estimated to provide approximately 13,000 cubic yards per year. It's not unreasonable to use a ballpark figure of around $20 if that material had to be purchased from a quarry and trucked into the shoreline. And so that would give a replacement cost of well over $200,000 per year. Of course, this is an oversimplification. As was talked about, many of this material is fine material. And of course, there's the land being lost to erosion does have value as well. However, it does stand to reason that incorporating some consideration of sediment replacement cost into shoreline management decisions is a good start, as these inputs do have value. Next slide, please, David.
Yep.
Thanks. Yeah, so in addition to the reasons I just mentioned, there are recommendations for further characterization of impacts and opportunities related to shoreline management, sediment supply, bluff conservation, natural resiliency. And these recommendations are found in federal, state, and locally based plans. For example, the proposed study is aligned with recommendations within the Army Corps' Great Lakes Overview National Shoreline Management Study. It's also supportive of Goal 5.1.3 in the draft Great Lakes Action Agenda. And this type of study was identified as a top priority in the Wayne County CLEAR initiative, the Coastal Lakeshore Economy and Resiliency Plan. Next slide, please, David. Yeah, so as I mentioned, we're really at the beginning of this process, but I said that this is intended to build on ongoing and existing efforts, including the core budget, the CLEAR initiative, but working with some of the partners that you see here, DEC's programs, DOS, New York State OGS, Parks, TNC, Sea Grant, and Army Corps, and other local stakeholders. We have identified some initial project goals, which include further detailed characterization of these feeder bluffs and the inputs and the system impacts, and generally advancing the understanding of the regional sediment sources, sinks, and pathways, and what sort of impact they have on the vulnerability of these sediment dependent coastal features. I think there's room to look at dredge material management and potential bypass options, and really to better understand general offshore losses and also harbor structure impacts. A key goal of this project is to identify demonstration projects and conservation opportunities that would preserve and restore sediment supply to the natural protective features. So I think David and I would both welcome any feedback on what we've discussed and certainly any questions. Thank you.
You, David, and
Yeah.
you.
Yeah,
Well-
David, what happens to that longshore drift at the harbor mouths or the inlets? Is there a lot of, there's a lot of import into the shallow water?
I guess the Army Corps sediment budget is depicting those as deflected into the deep lake and lost to the longshore flow.
Okay, thank you.
Jeannie has her hand raised.
Hi, I have a question about the long-term sustainability of the feeder bluffs and how has it been modeled at all in terms of how long can those bluffs be actually feeder bluffs, and do they also receive some kind of building process that sustains them, or it seems like something that won't last forever?
Well, they do go through a life cycle. The erosion, the provision of sediment to the longshore current seems to be most prevalent during the mature phase of the bluff. But you're raising an interesting point. Yes, these bluffs do as they pass through the mature phase, their erosion slows down, but they're not forever. No. The Great Lakes are net erosive. They're always getting bigger.
Yeah,
I don't know if
Dave,
And they're presumably they're also building, they're also constantly building. So it's a changing shoreline all the way around, I suppose.
Well, yes, they are creating beaches and offshore bars. It's not just the beach itself. It's out into the water, the whole near shore and land-based land-water interface. The beach is one thing, but that's built by this longshore transport, but also the sandbars and the patterns of water movement offshore, which are key factors in the life cycle of many fish and aquatic insects.
yeah, David, I guess just to add to some of what you just discussed, there was a paper that I think Sea Grant sponsored from the early 90s. I think David might have been referring to that sort of talks about that life cycle of these, particularly these drumlin systems and how they contribute sediment over time. But I think it's also a matter of time scale. I mean, if you look at average erosion rates for a bluff, and then you can map out that feature and look at the inland extent. So I mean, you might be talking about a drumlin that could contribute sediment for hundreds of years.
Yeah.
And then you can also, just looking at a topographical map of that region, I mean, there's additional drumlins that are on inland, and there's drumlins that were at one point in the lake, which are now gone, and we see remnants of them on the lake bottom. So certainly the shoreline is dynamic.
Yeah, very interesting. Thank you.
We do have one question from the chat. And this is for David Clark. Has DEC remapped the CHA of the Great Lakes region?
I'm not directly involved with that process. I could certainly get you the contact of folks that are. I know there's been some analysis of shoreline erosion rates, but from what I understand, the current regulatory CHA maps are the same ones that have been in use for many years. And if you'd like to follow up on that with me, feel free to send me an email, and I can put you in touch with the correct people.
Okay, with that, I think we should just keep on moving. So Kathleen, you want to introduce Army Corps?
Yes. So next we're going to have Danielle Tomaso and Dana Rose Brown from the U.S. Army Corps of Engineers. And they are going to talk about their regional sediment management investigation that they're currently doing on the North Shore of Long Island. So Danielle, you want to go ahead and share your screen? You can take it away. Danielle, it looks like you're unmuted. I'm not sure if you're speaking. I can see your screen, but I'm not hearing any audio.
Great. Can you hear me now?
Yes, perfect.
Okay, great. Thanks everyone for your patience with my audio. My name is Danielle Tomaso. I am a planner here at the New York District Army Corps of Engineers. Just quickly, can you see my screen?
Yes.
Great, great. So I'm here this morning with Dana Rose Brown. I will let her introduce herself when we get to her part of the presentation. But what we want to share with you today is the work that we've done on the North Shore of Long Island Regional Sediment Management Investigation. This is funded through the Army Corps' Regional Sediment Management Program, which we'll talk about later in the presentation, but I just want to let everybody know this is an R&D type program with an annual call for ideas for investigations like the one we're going to go through today. So certainly if anyone's ever interested in partnering with the Army Corps on an investigation like this, we would be happy to talk to you about that opportunity. So just quickly, again, Dana Rose and I are just two of half a dozen people on our team. Those in New York might see some familiar names like Frank. I know Rune, Mom, and Katie are new to the team, but a lot of folks know Frank who couldn't be here today. But we'll go through the work that he and Dana Rose led for this investigation. So just quickly, although this investigation isn't specific to Bluff, we want to share today about what we've been doing because the Army Corps is hoping to look at regional sediment management in a comprehensive way and looking at Long Island as a whole. We know that Long Island, regional sediment management on Long Island is very challenging, and the North and South Shores are very different. So on the North Shore, which we're talking about today, we have many bluffs, rocky beaches, pebble beaches, and harbors. It's very different from Long Island South Shore, which is more sandy beaches, barrier islands, and back bay environments. So two very different environments. The Army Corps New York District has been very involved on the South Shore with a lot of traditional beach and dune renourishment work. The North Shore is a little bit more complex, which we'll get into. So we decided through this investigation to focus on the North Shore because we know a lot about the South Shore, and we actually had a regional sediment management investigation a couple of years ago that was funded to look at the sediment budget of the South Shore. So we're doing the baby steps of completing the sediment budget on the North Shore through what we'll go through today. So the objectives that we did for our one-year study is to investigate and characterize to the extent practicable Long Island's North Shore coastal environment, just using existing information. There's no modeling done, things like that, surveys or anything. The second piece of the investigation is to identify ways to better incorporate regional sediment management into coastal management. So we know that there are ways to more efficiently, effectively use sediment in the system for ecosystem restoration projects, for coastal storm risk management projects, and for navigation. So we thought about these things throughout our investigation, which DR will talk about later. Our third part of our investigation, I think one of the more important parts is to collaborate with stakeholders. We have what we call the Long Island Regional Sediment Management Working Group that was established in 2019, about a year before the pandemic. And Henry has hosted our group just this summer. It was really good to see everybody, but we're hoping to keep a line of communication open with stakeholders throughout the region to talk about regional sediment management, to align with the goals of this investigation and just generally with the Army Corps' hope of managing sediment in an efficient manner on Long Island. And then the fourth thing I just want to point everyone to, we're summarizing our findings in this investigation in a technical report that will be published hopefully next year. So keep an eye out for that. You'll see all the technical details DR and I will go through today in that technical report. So I talked about a lot of this, but you'll see on the bottom a map of Long Island for those who aren't too familiar, maybe all Great Lakes folks. So we're the big island next to Manhattan, not to be silly, but it is a very long island. It's about 120 or 150 miles as the crow flies. So we looked at the entire extent from here in, this is Queens County, so part of New York City, all the way through Nassau County and Suffolk County to the tip of Long Island. And again, I mentioned we used existing information for this. So we relied on a lot of academic research, a lot of past Army Corps studies. We didn't do any surveys or modeling or other data collection like that. So what DR will tell you about is really what we hope is a comprehensive summary of the science done to date on RSM on Long Island. So our first step was just identifying some problems, needs, and opportunities, constraints and considerations. You can see here, basically, we see, and this is no surprise to anybody who lives or works on Long Island, but you see a lot of shoreline and bluff erosion on the North Shore. Infrequent inlet dredging contributes to problems. There's just not enough funding, we're hearing from locals, to dredge the inlets as much as they think they should be dredged. And these two things lead to a deteriorated shoreline stabilization structures like jetties and groins. And so all of these problems have compounded into what you see on the North Shore today. Just another map to get everyone acquainted with the area. I wanted to point out some Army Corps studies and projects for those who've been involved in the work, just so you could see the Army Corps has done a lot of studies in the area, especially after Hurricane Sandy. We looked at coastal storm risk management in Bayville and Asheroken. Also in the communities of Wading River, there's Wading River Creek in the Shoreham area, Goldsmiths Inlet out in Southold, and Hashimomic Cove out on the North Fork. So this is call it the Army Corps footprint. Again, I use the word studies. We haven't done a lot of coastal storm risk management work like the Army Corps has done on the South Shore. I mentioned that on the South Shore we have a bigger footprint, a lot of traditional dune and beach projects. We don't have so much on the North Shore. but are certainly studying ways to work with partners to do potential projects on the North Shore. I also want to point out some of these stations that DR will be mentioning in her presentation that we grabbed information from. So we did a literature review, like all good researchers should do, and as a step one. And again, we just summarized all of the existing information that we could come across, anything about academic studies, data sets, sediment transport studies, any projects of studies that I mentioned on the last slide, a lot of literature from Stony Brook University, from the major researchers listed on the screen. So this really helped us inventory what we see on the North Shore. So I talked a lot about what we did, but I want to turn it over to DR now, who's going to go into the nuts and bolts about what we found on the North Shore.
So as Danielle mentioned, my name is Dana Rose Brown, and I'm a coastal engineer with the New York District, and I was one of the coastal engineers involved in this investigation. There isn't a lot of existing information about coastal processes on the North Shore of Long Island, so we start our investigation by creating a coastal structure inventory to help characterize the shoreline. The coastal structure inventory was created visually using Google Earth to identify shoreline stabilization structures on the North Shore of Long Island coastline. And a map of that structure inventory is shown here, where you can see groins, revetments, jetties, harbors, inlets, and more, all labeled on the North Shore. And this inventory allowed us to see where shoreline stabilization measures have been implemented and how they are functioning today. Next slide, Danielle. So the North Shore of Long Island is a glacial deposition coast characterized by non-uniform coastline with stretches of sandy and rocky beaches that are split up by many harbors, bays, and bluffs. As you can see in this figure, much of the North Shore coastline consists of bluffs ranging from 10 feet to over 150 feet in height, and many of these bluffs are fronted by rocky and sandy beaches, which help protect the bluffs from direct wave attack. And much of the North Shore is compartmentalized into smaller circulation cells between these headlands, inlets, or different structures. And bluffs are the largest source of sediment to the North Shore beaches. And as they erode, sediment is predominantly transported offshore or oscillates within these circulation cells, or within the circulation cell which that bluff is a part of. And as fronting beach material is removed, it increases the exposure of the bluff to waves, and eventually the bluff erosion supplies new material to the beach and the cycle continues. Bluff erosion on the North Shore is also driven by high water levels, which can lead to bluff collapse, or overland erosion, which removes vegetation and weakens the bluffs. It's also important to note that a significant portion of the bluff coastline on the North Shore has some form of stabilization measure, which directly impacts the natural sediment supply to the littoral system through erosion. So we created what is basically an engineering appendix to characterize coastal processes and marine forces along the North Shore. So wave and wind data was collected from 2 National Data Buoy Center, or NDBC stations, and tides and water level data were collected from 2 National Ocean Service, or NOS stations. And an example of that data is shown in these wind roses. So sediment transport data was also collected along the North Shore from existing literature and studies, and coastal storm data is collected from the North Atlantic Coast Comprehensive Study, or NACCS. So on the North Shore of Long Island, erosion and accretion are mainly attributed to wave action along the coastline. And as I said, the wave and wind roses for the western end of North Shore are shown here. And they show that the dominant wave and wind direction in this location is from the west and west-northwest, where the largest waves are generated that impact this coastline. And knowing the types of waves that impact the North Shore help us understand how these waves impact coastal erosion in this region. And 2 tide gauges were selected to look at maximum and minimum recorded historic monthly water levels on the western end and on the eastern end of the North Shore. Here you can see that there are some variations between the eastern end and the western end, with the western end of Long Island Sound experiencing tides of a greater magnitude than the eastern end. And on this figure, we can see some extreme high tide events, which are indicative of large storm events that can cause greater levels of erosion. And using data like this, we can better understand the magnitude, duration, and occurrence of high erosional events. Here, the estimated relative sea level change at Kings Point, New York is shown, with approximately 1.5 feet of relative sea level change predicted for the intermediate projection between now and 2100. And under the high scenario, the increase in sea level is even greater, with a change in relative sea level of 4.5 feet. And these increased sea levels can lead to an increase in erosion along the coastline, highlighting the importance of coastal storm risk management. As sea levels continue to rise, it's expected that bluff erosion on the North Shore of Long Island will increase. And with rising sea levels, beaches may become more overtopped more frequently, which will leave bluffs more vulnerable to wave action than before. Another piece of information that was useful to our investigation was sediment transport and erosion rates. Some accretion and erosion rates for the portion of the Long Island west of Wading River are shown here, taken from the North Shore Suffolk County Beach Erosion and Hurricane Control Interim Study. And as you can see, there are many nodes where transport intersects, and these are areas where we see accretion on the North Shore. However, most of the beaches on this western portion of the North Shore are experiencing erosion. And then in this figure, we see erosion accretion rates for the eastern end of Long Island. Transport on this end of the North Shore is predominantly to the east, with less nodal shifts in complex harbors. But even still, we similarly see a mostly erosional coastline along this section of the North Shore. We also included data from available sediment budgets for Asher Oak and Mattatuck Inlet and Bayville in our study. However, there's limited sediment transport information available for the rest of the North Shore. So the North Shore of Long Island is a complicated transport environment due to its convoluted coastline, especially on the western end of the island where there are many harbors, tidal creeks, and inlets. The complicated transport regime on the North Shore is an added challenge for us when we were identifying sediment sources and also for creating a sediment budget in the future. The North Shore is especially complicated compared to the South Shore of Long Island, which has some nodal changes throughout, but generally experiences transport from east to west with interruptions at inlets. And the North Shore is much more complex with multiple nodal shifts and harbor complexes. So it's just an added challenge when looking at this for the North Shore. And in addition, there's just less information available related to the North Shore in general. Where information was available, we looked at sediment budgets and dredging and placement records to identify potential sediment sources along the North Shore of Long Island. And identifying federally owned and maintained inlets on the North Shore played a key role in our investigation, as these inlets can provide sediment sources and opportunities for beneficial reuse for CSRM or restoration objectives. And some of the existing information we were able to extract from these studies includes past dredging records and surveys at these federally maintained inlets. And so if you're interested in reading more about our investigation, the draft technical report is completed and it's expected to be published in 2023. Or if you're interested in working with us, there are opportunities for future regional sediment management investigations. Or another way to get involved, as Danielle mentioned, is by joining the Long Island RSM working group. And if you have any questions or want to get involved, mine and Danielle's contact info is shown here. So thank you, and any questions?
Thank you both. Looks like David Klein, you have a your hand is up.
Yeah, thanks. I guess about a year and a half ago, I read a detailed study focused on the Mattatuck Inlet, which concluded that the jetty structure at that inlet had created quite a sand shadow to the east, and it called for transport of sand around the inlet, around the jetty, and placement east of the jetty structures. Did that ever happen? And I was interested to see that your study doesn't seem to consider Mattatuck.
We did consider Mattatuck. I don't know the exact answer to your question. I don't know if Danielle does, or we can get back to you with that.
Henry's raising his hand. He seems to want to say something.
You need an old guy to answer that one. No, it never happened. The people to the west of the jetty vigorously objected to taking away their beach and moving it east. That was mostly a state initiative.
I think that there was, I know you asked about Fisher's Island and Danielle answered him, but there was one more question in the chat from Nicole Marr, asking if you could explain how infrequent navigational dredging of inlets leads to destabilized shorelines.
Oh, yes, and I should have said that our investigation, so I'm sorry, infrequent navigation dredging, we looked at the effects of the infrequent navigation dredging in the area on coastal navigation structures, so groins and jetties in the area. And we saw that when an inlet isn't dredged very often, you see patterns of the coastal structures around them. They get degraded. You know, you'll see two jetties fronting an inlet, and you'll see that kind of what Henry was just alluding to. One side is you get the buildup, and the other side you don't see the buildup, and it's caused structural problems to some of the coastal structures in the area. I don't know, DR, if you want to expand on that.
No, I don't really. I'm trying to understand the question a bit better. Can you repeat that again?
The question was if you could explain how infrequent navigational dredging of inlets leads to destabilized shorelines.
Okay. I mean, more so for us, there's just an issue. It's an issue of infrequent dredging can cause buildup within those navigational channels. A lot of the time that sand is then reused and placed on beaches. So it's more just we keep kind of keep up that process and keep maintaining those channels is better for keeping, maintaining beaches and having that sediment supply to them. Because in some cases it all builds up, as like Danielle was saying, can cause issues with our structures, as sand will build up on one side and it can lead to issues where they need to be maintained.
Thank you. I see you, Corey, but I'm going to ask Brian's question first. He was wondering if you have ground truth, the shoreline structure inventory, that it might bulkheads and seawalls might be more extensive than the numbers suggested.
Yeah, we have not ground truth that. So it's definitely was for this investigation, it was more of, like Danielle said, R&D, very top level, just kind of getting an idea of where sediment is available. And yeah, we were not able to ground truth that. I agree. There could definitely be more bulkheads and seawalls that were not visible through Google Earth investigation.
Corey, just before you go, I want to just draw everyone's attention to Roy's comment in the chat. We're now transitioning to the panel discussion, so feel free to ask questions to all of the presenters, either in the chat or by raising your hand. Okay, Corey, now you can go. Thanks.
Thank you, appreciate it. Everybody knows I'm kind of jumpy on the trigger finger here. My question is kind of, I guess, for all the panelists. I'm happy that I'm now able to ask everybody. At the district, we have a tough time identifying parcel map when it comes related to Bluff. So when an evaluation needs to occur, it's challenging for us to determine where the top of the bluff would be. And more importantly, whose land am I standing on when I'm staring at the top of the bluff? I know there's been some questions going back and forth of, does this layer even exist in GIS? Does anybody know where the property bounds actually are? Are there still tax map numbers that have maybe slid down the slope already? We just don't know. So I guess it kind of plays into Brian's question about the inventory of not only structures, but maybe inventory of who owns what in some of these areas would be, in my world, critical. I just didn't know if anybody had an answer to that. Is there like a database available or something like that?
Corey, doesn't the planning board, Long Island Planning Board have that parcel map? I know I've seen one somewhere, but not electronic, just printed.
I'm not sure, Henry. I would imagine they should, but when the investigations that we've done, and again, investigations, not what y'all are doing. But what we're having trouble is actually determining in some of the North Shore communities, for example, Sound Beach is a big one that Kathleen and I have worked on, is who owns the beachfront, who owns the bluff, who owns the top. It's, for us, it's challenging to get all the relevant players or, vested interest parties together. We don't know who owns what and everybody points a finger. So
if I could speak up, this is Dennis Cole. The Suffolk County GIS, which is down now because it was hacked, has parcel information overlaid on several layers. Once it's back up, that information is available. There's also another source through the Suffolk County Real Estate Office. It's you have to pay to use that service. And some of the townships have parcel information as well. So there's various sources available, but right now it's difficult because Suffolk County GIS layer is down.
I guess, that's great, Dan. I appreciate that. But I guess, the real heart of the question is, we're having trouble identifying where the top of the bluff is. So we can have the tax map parcel numbers, we can have the GIS layers, but when we go there, it's just, there seems to be a confusion of who owns what, who has jurisdiction of what. And to my knowledge, I don't know if there's been a coast-wide bluff evaluation of just the line. Where the heck does the top of this thing start? Where does it end? I think that would be critical for all the work that we're doing. But again, maybe I'm overseeing something that's obvious to everybody else.
I guess you could probably use, there is another layer that's on the GIS that has the topos, the 2-foot contours.
Mm-hmm.
You could use that, to look at the top of the layer, then compare it to the parcel line. Remembering, of course, that, when the parcels were created, there was always a level of error established in the exact precise location. They never exactly matched the surveys, but they're pretty close.
Yeah, I think, just given a real world touch to it, we often get requests from municipalities of saying, hey, can you all run out and let us know this, this pool was 100 and, the pool was 90 feet from the top of the bluff. And we get there and we're going, yeah, that might be according to your tax map, but I'm counting 27 feet from the edge of this pool house off the end of the cliff. So maybe that's something that we should all put on our radar to maybe have a separate conversation on, is to ground truth it a little bit better, or maybe find some other technology to really map that out. That would make my life a lot easier for me, that much.
I know for DEC tidal wetlands, the common standards change if we have jurisdiction on the bluff. You would keep going until you hit an area that's slope is changed to 1/5. And we have that as basically the, I guess, unwritten rule for being able to tell when it switches over. So if you have 2-foot contours and you're using a map, you just scale it off and find it. Look to see if for every given foot that it equates to 5. And then that snapping that line is, at least for tidal wetlands for DC, is what we consider top of bluff.
I guess that leads, does everybody feel that resolution is appropriate? Or is there another method that we can possibly go about working this up? Because it sounds logical in my mind. See, I did ask the right question, Kathleen.
And there's a couple of comments, if you've been following the chat, about the GIS property lines and towns having information, and also the CHA line maps.
It definitely seems like a local issue throughout New York State, because that's going to be your towns and counties collecting that kind of data. So Corey, you work in one county, so that should be hopefully a little easier working with one county instead of Kathleen and I that probably have about 15 or so to work with. But that would be a good thing to have, is just where to go for some of this stuff. And there was a comment in the chat that finalizing the CHA maps would determine the top of the bluff, since they are natural protected features. And also there's another one earlier on about DOS is currently digitizing the CHA maps as well. Of course, not every community is CHA, so there's that. We have any?
Boy, they're digitizing the original CHA maps.
I'm wondering the same thing.
Yeah, I can't answer that. That would be a DOS or DEC question, I believe.
I'm not sure if Carrie, if you want to clarify, or maybe she just did.
Portable GIS units and regular monitoring is what you need to do. Top of the bluff is a moving target. The original CHAs are being digitized.
This is Rebecca Newell from Department of State. Can I chime in for a second? Because I
Absolutely.
actually private messaged Carrie. I supervise the GIS unit at the Office of Planning, Development, and Community Infrastructure. And I'm not aware that we are digitizing the original CHAs. So I actually posed a question privately to Carrie if she could let me know where she heard this, or if she knew who was doing it. I don't know if it's something through our buildings and codes and not through planning and development, but that's not something we are currently working on that I'm aware of.
Hi, this is Aram from First Coastal in West Hampton. Those original CHI maps are scanned and available from the DEC. I make a request and they'll give them to you.
Thanks, Brian, I see your hand is raised.
Hi, Kathleen, everybody. I had attended I guess a workshop is the best word for it, back in 2016. I think Aram was in that meeting as well at the Quag Firehouse in out on the east end of Long Island, where they were kind of showcasing the new draft CHA maps. And they seem to be, I don't know if there were some panels that were not completed yet, but they seem to be pretty close to getting ready to roll them out for public. 2017, that time frame. A lot more street maps are on them than there were in the 1980s when those maps were drawn up. They were ortho-rectified for GIS and generally have a lot more information on them than the old CHA maps do. So I know they're in the hopper somewhere, or they're under development, and it would be good at some point to get them out, even in draft form, as a planning resource.
Thank you, Brian. David Klein also has his hand up.
Yeah, thanks. I don't want to miss the opportunity to ask such a knowledgeable crowd what you'd be looking for in the study that David Clark introduced. This will be a study to take the Army Corps sediment budget to the next level of detail and enable specific, specific tailoring of conservation projects to areas that are playing a key role in the process. What would you be looking for in such a study? Any input would be very valuable.
This is Jeannie. I would be looking for better or more accessible delineation of private versus public, access, or along shorelines. For instance, if the public is interested in walking along a shoreline, where's the public-private line? And are there opportunities for communities to perhaps have a walkable shoreline resource where that line falls in a reasonable way to allow them to do so?
Brian?
I think some of that gets into the public trust doctrine, which I'm not anywhere close to being an expert in, but I believe in general below the mean high water line, you start getting into the public domain, and the public has a right to foreshore passage. I think it gets a little trickier for a lot of the dry beach areas between the whatever upland feature, the seawall sometimes behind it. But we don't, we probably don't, as a planning group, discuss the importance of the public trust doctrine in discussions like this.
Exactly. And it would be great to have the public trust doctrine line mapped. Even if that's a moving target, every once in a while, it'd be great to have it mapped.
Now, we just tried to do that, map out the mean high water line for a section of the coast here. It really is a trick because you can find the mean high water elevation, but the damn beach keeps moving around. You draw a line, the beach moves out from under you.
Yeah, and if you do the measuring by aerial or in person, it's hard because you'd have to guarantee you're there at high tide, not low tide or mid tide or storm high tide or Hurricane Sandy high tide, or it's so variable, and it's probably only good for the, I don't know, quarter of a moon cycle.
Well, you can get an absolute value for the mean high water elevation but you need long tide gauge records, and then you can find that elevation.
I think I think the time frame is 19.7 years of data, and that'll make for a true mean sea level, or mean high water, or mean low water.
Yeah, well, you can do it from shorter records if you can tie it to a long-term statement. It's a involved process, but NOAA has it all worked out.
Challenging. but it could be really valuable for communities looking for, public access where land has been completely privatized and very tiny little areas of public access left available. It's something of interest to my communities for sure.
Usually down here on Long Island, the issue with access points is the question of you go to a street end and is the staircase down to the beach privately owned, publicly owned only for people of that town. That's usually it. There's not necessarily straight access at street ends to get to it, but as long as you can go over public land to get to that high water line, my understanding at that point, you can walk as long as you want within that intertidal zone. You might get your feet wet,
Right.
but that's your
Right.
that's your zone that you're allowed in.
A great discussion. Brian, I'm assuming that's an old hand, or is it a new one? We're getting close to the top of the hour here. Just wanted to do a quick time check so we can make sure we're wrapped up and finished in time for lunch. So I guess with that being said, is there any last burning questions before we wrap up?
Yeah, I would like to ask again if anyone is aware of any beach profile, like bluff profile data for particular, like a historical profile. That would be a great, I think, help for us for making our research more applicable to the real life situation. So we need to eventually validate, whether the recession or the beach profile would evolve using our model the same as it does on the beach. So, and I know some individuals might have done some survey, but I don't know if there is a more organized research on this issue, by the Army Corps of Engineers or.
Well, I know based on tidal wetlands regs, what we use is if you don't have enough evidence, say an old survey or some other means, our regs say that you default by going to the most recent quad map USGS surveys to look for it. And those you can usually find free versions online just by searching like USGS quad maps free, and you can find them pretty often. The best one, I can't think of the name of the website, but it's one of the top ones if you Google it, has usually back to late 1800s through to the last decade. How many of those have contours? It's definitely a lot more. The more recent you get, the older you get, it's more what you'd expect for a 1904 survey. But you probably get contours from, say, the 60s to now. You can find those on quad maps.
Hey, Ali, this is Aram from First Coastal. What you're likely, if for the most detailed information, you have to go down to the parcel basis where people have done topo surveys. And so in order to get that data, you have to foil the local municipality and get their subdivision map or their building permit file. So what I would recommend is that you target the area that you're interested in and then investigate if there is data available, like topo maps that you could convert into profiles.
Mm-hmm.
A lot of the old subdivision maps have topo, and they were subdivided a long time ago, so they provide a really good basis. And then like recent building permits in the subdivision will show you a lot of times a change in the bluff location. But you have to really target the area you're looking at because it's a deep data search.
Got it. Thank you very much.
Yeah, you won't, like, if you send in a foil with hundreds of sites, you're probably gonna get something bouncing back that it's too broad. It's gonna take staff way too long. But you could batch them, like, I don't know, send one in for 5 or 10. Once you get those back, send one in for 5 or 10 and just keep working it that way. Then it's not as massive of a drain on staff time at whatever agency you're foiling.
Yeah, I mean, Ali, reach out to me offline and I'll show you how we do it.
Sure, will do. Thank you very much.
Ali, I'm not sure how far back you're looking for profiles, but you probably know, at least for Lake Ontario, there's topobathy LiDAR data sets that go back to, I believe, 2001. So that's, 20 plus years where you could extract profiles along a transect.
Yeah, no, I'm aware of those data. The issue is we need like a bathymetric data too, because we are looking at not just necessarily on the dry part of the bluff. Also, we want to see how the beach and the shoreline, not necessarily the shoreline, I mean the bottom of the sea near the bluff evolved. So the LiDAR data are obviously for the dry part.
Well, these are Army Corps topobathy LiDAR, so they do penetrate the water column to various depths depending on different factors. But
so it's available for do you know like how often they've been?
I think I defer to the Corps, but I think they like to do it every 5 or so years. I know in Lake Ontario there was regions that were mapped in 2001, 2007, maybe 2011. 2018, and so there's quite a few, and they're available on NOAA Digital Coast.
Oh, I see. All right, sure. Thank you for that.
Okay, do we want to wrap it up?
Yep. I think so. It's a great discussion, great presentations. Thank you to all of our presenters. Feel free to reach out to any of them with any follow-up questions. This symposium was recorded. We will be making a link, so please contact me if you would like to have a link, have a copy of the recording. Roy, any last final words?
Nothing from me, just aside from thanking the speakers for being a part of this and for the really excellent turnout that we had today. I believe we had 61 on at one point with 76 registrations. So we did really good, and it's really great for us to see that this is very much an issue that all of New York State is dealing with, and that the omnibus research that we funded reflects that, and the extension work that Kathleen and I are doing will probably keep up with that as well. So thank you all for coming.
Yes, and reach out to us if you're interested in some copies of the Blufflet.
Thanks,
yeah, it's gonna be sweet.
Everybody else. Thank you.
Thank you.
Thank you.